Hi, this video will be about an application of the convolution property of the Fourier transform. And in fact, it's an important application because it explains why we name the Fourier transform of the impulse response of a stable LTI system as the frequency response. Now remember that if we have a linear time invariant system with input x of t and output y of t, the output is the convolution of the input with the impulse response. This is the general result. Now, if the system is stable, we are able to use the convolution property of the Fourier transform to express this convolution expression in frequency domain as follows. Now, let the LTI system be stable. That is, the integral of magnitude of h of t is finite. H of t is absolutely integrable. So Fourier transform of h of t, which is called h of omega, which is the Fourier transform of h of t, exists. And remember, h of omega is called the frequency response of the system. Frequency response of the system. And we are able to express y of omega as x of omega multiplied by h of omega. Of course, here we assume that the input x of t is also absolutely integrable and its Fourier transform exists. Therefore, y of omega can be calculated easily as a multiplication of the Fourier transforms of x of t and h of t. So the convolution operation in time domain reduces to multiplication in frequency domain. Now, first of all, let us explain why we call the Fourier transform of h of t as the frequency response of the system. Now, consider the case where x of t is the complex exponential signal e to j omega 0 t. So omega 0 is a constant. We have a constant frequency and we have the complex exponential signal. Now y of t is the convolution of x of t and h of t. Now, we have seen that the convolution operation can be easily handled in this case because e to x of, first let us write this as x of t minus tau, h of tau, integrated with respect to tau. So this is equal to e to j omega 0 t minus tau h of tau d tau, and e to j omega 0 t can be taken outside the integral because the integration is with respect to tau, from minus infinity to plus infinity, e to minus j omega 0 tau h of tau d tau. But as we see, this expression, this integral, is nothing but the Fourier transform of h of tau evaluated at omega equal to omega 0. So this is h of omega evaluated at omega equal to omega 0. In other words, it is h of omega 0. So y of t is equal to h of omega 0 e to j omega 0 t. Now this analysis is in fact an explanation of the name given to the Fourier transform of h of t. The name is frequency response, and we clearly see that when the input is the complex exponential signal e to j omega 0 t, the output is the same complex exponential signal but multiplied by a constant, because omega 0 here is a constant. So we evaluate the Fourier transform at that constant frequency, and therefore h of omega 0 can be interpreted as the response of the system to the complex exponential signal with frequency omega 0. That's why it is called the frequency response of the system. So we have interpreted this result as follows. We have a stable system, LTI system, and we have to be sure that it is stable. If the input is e to j omega 0 t, the output is h of omega 0 e to j omega 0 t. So essentially the system action leaves the input signal invariant. The signal occurs at the output, but it is only multiplied by a constant. This constant is of course a complex constant, meaning that the magnitude of the input signal is modified, and we have the phase occurring at the output, the phase term occurring at the output. So we have a change in magnitude and in phase. And we have also interpreted this result as the eigenfunction property of LTI systems. So for stable LTI systems, complex exponential signals are eigenfunctions. That means they are essentially unchanged, only scaled, multiplied by a scalar, by a complex constant. Okay, so how can we obtain the same result by using the convolution property of the Fourier transform? So let us look at this problem next. Okay, now in terms of the convolution property, the problem can be interpreted in the following way. Now, h of omega is equal to the Fourier transform of h of t okay, we know that the system is stable, therefore h of t is absolutely integrable, and therefore the Fourier transform exists. Now, the input x of t is the complex exponential signal e to j omega 0 t. Now, therefore, x of omega is equal to, we know that the Fourier transform of the complex exponential signal is 2 pi delta of omega minus omega 0. So, the Fourier transform of the output is the product of x of omega and h of omega. So we have 2 pi delta of omega minus omega 0 multiplied by h of omega. However, we know that the impulse is 0 everywhere except at omega equal to omega 0, where it is infinite in magnitude. Therefore, this can be written as 2 pi delta of omega minus omega 0 h of omega 0. Okay, so h of omega is a function of omega, but we know that the impulse is 0 everywhere except omega equal to omega 0. Therefore, only the value of h of omega 0 is taken into account. So, by using the fact that the Fourier transform of the complex exponential signal is 2 pi delta of omega minus omega 0. So we have only a multiplication by a constant. So by the linearity property, we have h of omega 0 e to j omega 0 t. And we have obtained the same result as expected. Okay. Then, as an application, let us do the following. Let us assume that x of t is a signal which is a superposition of complex exponential signals, and we will be able to use the linearity of the Fourier transform to find the output in that case. In fact, we can apply this directly to the to a periodic input signal with a Fourier series representation. So let x of t be a periodic signal with fundamental period t0. Then we know that x of t will have the Fourier series representation, k running from minus infinity to plus infinity, ak e to j k omega 0 t. Here, of course, omega 0 is related to the period of the periodic signal by means of this expression. So, again, we assume that our system is stable with frequency response h of omega. So, first, we claim that this x of t is the input signal. X of t is the input signal of the stable LTI system with frequency response h of omega. So y of omega will therefore be equal to x of omega, h of omega, by the convolution property. X of omega is the Fourier transform of the Fourier series, which is k from minus infinity to plus infinity, ak 2 pi delta of omega minus k omega 0. Okay, and y of omega is therefore equal to k from minus infinity to plus infinity, ak h of omega 2 pi delta of omega minus k omega 0. And in fact, again, we know that the impulse delta omega minus k omega 0 is 0 everywhere except omega equal to k omega 0. Therefore, this omega can be replaced by k omega 0. So this becomes k from minus infinity to plus infinity, ak h of k omega 0. Okay, we have 2 pi delta of omega minus k omega 0. And we can directly evaluate the inverse Fourier transform as the Fourier series representation of the output, k running from minus infinity to plus infinity, ak h of k omega 0 e to jk omega 0 t. So we interpret the product ak h of k omega 0 as the Fourier coefficient, the kth Fourier coefficient of y of t. So we have seen this in the context of Fourier series, but in terms of the Fourier transform, again, we see the following important application of the convolution operation in time domain and the convolution property of the Fourier transform in frequency domain, implying that if the input of a stable LTI system is periodic with a certain Fourier series representation, the output turns out to be also a periodic signal with a Fourier series representation whose coefficients, Fourier series coefficients, can be evaluated in terms of the Fourier series coefficients of the input signal and the frequency response evaluated at the integer multiples of the fundamental frequency omega 0. Thanks for watching.